Welcome back, everybody. We're still talking about simple harmonic motion. Now we're going to get into some measurements that we can make with simple harmonic motion. And the first two are period and frequency. So take just a minute before you watch the next part. Refresh your memory on what your prediction for what a period is and what the meaning of period is and what the meaning for frequency is. Take that time, make that prediction. Now, you've made your prediction, we can check them. So the period, and for period, we use a capital T when we need to write this in an equation. The period is the time to complete one full cycle. So for example, the period of the moon's phases is 28 days. And the period of our planet's orbit around the sun is 365 and a quarter of a day, 365.25 days. And the period of the pendulum in a grandfather clock is 2 seconds. Once to go back, 1 second to go one direction, and another second to go the other direction. So the time to complete one full cycle, or the time before something that's undergoing simple harmonic motion, or periodic motion as well, the time before it starts to repeat itself. So it's the time before an object in simple harmonic motion or in periodic motion as well. The time before it starts to repeat itself. You catch that? What was my period there? 5 seconds before I started to repeat myself? Got it? All right. The time to complete one full cycle, usually we use the units of seconds on this. And then frequency, we use a lowercase f for this. Not a capital F, that's force, but a lowercase f here. And the frequency is how frequently or how many cycles occur in a given time, or in a set amount of time. And to measure this, we'll use units of, sometimes you would see like rotations per minute. Sometimes you see that with machinery. So if you're into woodworking at all, you might see that on like a table saw, how many rotations per minute. That's also something that's used in automotives. So your car has a gauge of rotations per minute for the engine. That's the thing on the dash that's going from 1,000, 2,000, 3,000, and you get it up to 8,000. Then your car starts steaming and the engine explodes. That's how many rotations per minute, or how many complete cycles it's making every minute. In physics, we're typically going to not look at how many per minute, but rather how many per second. And the unit is actually 1 over seconds, which is just read as per second. Or, more commonly, we use the unit hertz, and we abbreviate that just a capital H, lowercase z. Hertz, just like the donut. Ask me what a Hertz donut is. Go ahead, ask me what a Hertz donut is. Well, okay, I guess it doesn't do me any good if I'm not next to you. Okay, ask me in class what a Hertz donut is. You'll be really glad you did. Trust me, just ask. Yeah. Oh man, this is going to be sweet. So, period and frequency. Both related to how often or how much time these cycles take. So period and frequency, they have a lot in common. They both deal with how rapid simple harmonic motion is. But there's actually a set relationship. There's an equation that we can use to go from one to the other. And because I know how clever you are, I'm sure that you can figure out what that relationship is. So to help you with that, let's think about a situation where we have a pendulum going back and forth, and we'll say it's just a really quick little pendulum, and it goes back and forth pretty quickly, pretty rapidly. So let's say that pendulum has a period of 0.5 seconds. So it takes half a second to go left and right and then back again. Now, what would the frequency of that pendulum be? Take a minute, make a prediction. Don't worry, I'll wait for you. Got it? Oh, okay, I'll wait. Okay, good to go. So, what were we doing? Right, your prediction. So your prediction, what was the frequency of a pendulum if we know that the period is 0.5 seconds? The frequency would be 2. And the units on that are per second. You could call it cycles per second, oscillations per second, vibrations per second, or just per second is fine. Or 2 hertz. So we have a period of 0.5 seconds and a frequency of 2 hertz. What if we had a quarter of a second for our period? What would the frequency be then? The frequency then would be 4 hertz. Quarter of a second for the period, 4 hertz for the frequency. Take just a minute now. Write down your prediction for an equation that relates the period and the frequency for a pendulum or a mass on a spring or anything. It works for everything. I'll wait. Got it? Okay. The period and the frequency of anything, any oscillator that has repetitive motion or periodic motion, have this relationship that the period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. These two quantities are inverses of each other. I think this is our very first 2-variable equation. So this one is easier than what we're used to doing for equations. If we know one variable, we can solve for the other one. So if we know frequency, we can figure out period. And if we know the period, we can figure out the frequency. Now, what is it that determines the period or the frequency for a simple harmonic oscillator? We've done some work with pendulums before. In fact, that was the first thing that we did together. So I don't know, maybe you remember what influences the period of a pendulum already and what doesn't. But let's make a couple of predictions. First off, let's get a baseline here. So we use this pendulum. This is just a takeout Thai food container that's hung from a string that goes up to the ceiling. So the string is it's about 2 meters long. It's a little bit more than 2 meters, but 2 meters will work for our predictions here. So let's just get a baseline, figure out what the period is now. So just watch the timer down at the bottom of the screen here. Just watch the playhead, and I want you to figure out about how much time it takes to complete one cycle. Now let's do it by counting 5 cycles and then dividing that time by 5. So I'll pull this back just a little bit and start timing now. And there's 1, 2, 3, 4. Get ready to stop. 5. Stop. Okay. How much time was that? So get a number in your head. Divide that number by 5. That number is the period for this pendulum going back and forth. The time it takes to go back and forth just one time. All right, now I've got about twice as many, or about the same number of washers in my hand as I already have in this tub. So let's effectively double the mass, or about double the mass of this pendulum. Make your prediction first, though. Do we have any change in the length of the period here? What's going to go on? All right, you ready? Watch that play counter. Start. 1, 2, 3, 4, 5. Stop. Okay, what'd you get there? Divide that number by 5. All right. Nothing different, right? Same value as before. So adding mass didn't change the length of the period here. Now what about if we change the length of the pendulum? So let's say tie a knot up here. And I'm going to tie out, maybe 20 centimeters worth of my pendulum. Make your prediction again. Is this going to increase the period, decrease the period, or is the period going to stay the same? All right, ready? Watch your timer. And go. 1, 2, 3, 4. Get ready. Stop. How much time passed? And divide that number by 5. That's right. That's right. A shorter period for a shorter length of string. All right. Now one more test. What about amplitude? Does the amplitude affect the length of the period? So up until this point, I've been doing a fairly big amplitude like this. Let's do just a little tiny one. So let's come to rest. All right. This time I'm only going to pull it back like this. Make your prediction. Is our period going to be longer, shorter, or the same as that original period? Ready? Oh, hang on. Get a better drop here. That one was kind of wobbly. And go. 1, 2, 3, 4. Get ready. Stop! What'd you get for 5 periods? And divide that number by 5. Same as the original. Now, why would that be? It doesn't have to go as far, shouldn't it take less time? Who's think about that before our next class together? Why didn't the amplitude make it take a little more time or less time to go back and forth once? Why did the length of the string, and why didn't the mass? So we know the behaviors, we know the laws going into this. Now we want to work with the theory, the why of this part. We're also working with the mass on a spring for this unit for simple harmonic motion. So I want you to think about that system too. But we're not going to do that with the video. That's going to be an experiment we do, is what factors influence the period of a mass on a spring that's vibrating up and down. So maybe you think some of the same things as the pendulum could have an impact. Maybe the mass that's in here matters. Maybe the amplitude, which didn't matter on the pendulum, maybe it matters over here on the mass on a spring. What else can you come up with? What might affect this? Those questions, does this affect it, does that affect it? That's going to be the topic for our next experiment in class. We have one more measurement we need to talk about before we move on with simple harmonic motion, and that's amplitude. And for amplitude, we use capital A. If we need to write it in an equation, we use capital A. Amplitude is the maximum displacement that an object in simple harmonic motion achieves. And depending on the object we're talking about, we might measure that in meters. Say if we're looking at the mass on a spring, we could talk about how many meters it gets away from its starting point. Or sometimes we might classify that in degrees. So that's useful for a pendulum. How many degrees from vertical does it get? We might also consider simple harmonic motion in terms of the energy and the energy transformations involved. We know that we have this rule, this law, that energy is conserved for a closed system, and most simple harmonic oscillators, they do a pretty good job approximating a closed system, so energy is pretty well conserved there. So we can use that to figure out, say, the amplitude or maybe the maximum speed of some simple harmonic oscillator. So let's consider that now. Say we have a 2-meter long pendulum like the one that we have hanging from the ceiling in our classroom, and we'll have it pushed so that it leaves its equilibrium position at a speed of 3 meters per second. We want to know how far it's going to get, or how what the amplitude is for the simple harmonic motion that follows. So in order to solve this one, we're just going to say that our total energy initial has to be equal to the total energy final. And if we think about the situation, we initially have this thing pushed from equilibrium, and equilibrium is the lowest the pendulum can get. So at that point, it has a minimum value of gravitational potential energy. There's nothing mentioned here about stretching or compressing, so we'll say no elastic potential energy either. So initially it's really just got that kinetic energy from its movement. So kinetic energy initial, and then when it gets to its highest height or its farthest position, that's going to be potential energy, gravitational potential energy that it has because it's gotten up high. And so we can write out the expressions for kinetic energy and for gravitational potential energy. That should be a final, not an initial. We've got a mass on both sides here, so we can cancel those out, divide both sides by m. And so our height final then is going to be 1/2 v initial squared divided by g. And so in this case, our final height is going to be, let's see, 0.5 times 3 squared is 9, divided by 9.8 meters per second squared is 0.46 meters. Now this question didn't ask for the final height, it asked for the amplitude in degrees. So we need to think about this a little bit. If we had our pendulum hanging straight down, it would look something like this. Sorry, got the announcements chiming in here. And this is a 2-meter long pendulum. And when it gets to its farthest out position, something like this, we've got still a 2-meter long pendulum. So that hasn't changed. And now we know that this distance right here, from the height that it started at to the height that it ends at, that's 0.46 meters. So then we can just make a right triangle. I'll just connect this point right here. That's a right triangle, and we want to figure out the biggest angle theta that it gets to. So this distance I can figure out by saying, well, this total distance is 2 meters, and just this one little section, that's 0.46 meters. So this distance must be 1.54 meters. That's from here to here. And so then theta is equal to the inverse cosine of 1.54 meters divided by 2 meters, the length of our hypotenuse there. And so we get for our maximum value of theta a value of 39 degrees, 39.6 degrees. And looks like I just had one sig fig there, I guess, so we'll call that 40 degrees. is our maximum angle there. So the amplitude is 40 degrees. It swings 40 degrees to the left, and then it comes back to the middle, and then 40 degrees to the right, and so on like that. Thanks for sticking with us, folks. We'll practice with this in class tomorrow, and I hope that you bring any questions that you have with that, or comment in the video, comment below here, and I'll try and respond to those as well.